Hi folks, welcome back to Physics with Captain Rod. I'm making this video to help you work any of the homework problems that you're looking at having anything to do with curved banks. Cars, bobsleds, things of this nature undergoing some sort of circular path where the path itself is not level. So in this picture here, I've got kind of some snapshots in time of a car that's moving around this curve. Now in this example, I'm going to assume that the speed of that car is constant, so the magnitude of the velocity is not changing. And this curve has some sort of radius of curvature to it that I'm going to call R now in this description. And we're going to focus on this instant in time here. Now, because the car is undergoing circular motion, that means we're going to have an acceleration vector. I'm going to draw this in red. And that acceleration vector is going to point this way. That's going to be a centripetal acceleration due to the circular motion. Remember that centripetal accelerations always point towards the center of curvature, and that would be here in this picture. Magnitude-wise, this is calculated by taking speed squared divided by the radius. Now, if this car is moving along this path at constant speed, there are no changes in potential energy, no changes in kinetic energy. This is just not a work energy problem. So what this is going to be a Newton's second law type of problem, which means a free body diagram is going to be very important. So imagine now looking maybe from this viewpoint right here at this car. And I've already kind of drawn a snapshot here. Now the snapshot I have drawn would be if this were a level surface. And I'm going to go ahead and talk about that for just a moment. If this were a level surface, we'd have a gravitational force vector down. The normal, which would be the sum of four normals, the contact points in all four tires, would be vertical. And you'll notice that the acceleration vector would point to the right. So there's got to be a force responsible for that. In this case, that would have to be maybe a frictional force in this direction. So here's what the free body might look like if this surface were level. Now, if it's not level, if it's banked, right, then this picture may change something like this. Now I'm just going to use kind of a generic angle here. Let's say it's banked by some angle theta. How you work it's still the same. We start drawing our free body diagram. You're going to have a gravitational force vector. Now I'm not going to I don't want to get too far along because this is your homework problem, but the gravitational force vectors, they always point towards the center of the earth. That's down here somewhere. The normal force now, remember, normal forces have to make a right angle to the surface. So go ahead and put in your normal force. Now, whether or not there's a frictional force, it depends on the type of problem you're looking at. Imagine this car were going very, very, very slowly, and this is more a very, very icy surface. And what could happen is this car could effectively start sliding inward. So if the car's going relatively slow, your frictional force could conceivably be in this direction. If the car takes the bank way too fast, it would have a tendency in this picture to slide outward, in which case the frictional force would be this way. Some problems are about what's called the design speed. The design speed of a banked curve like this is the speed at which the car can take the curve with no frictional force at all. So if your question is about a minimum speed, you're going to want the frictional force this way. If it's about a maximum speed, you're going to want to put the frictional force in this direction. And if it's about the design speed, or if the idea is you want to be able to take it without friction at all, you're going to put no frictional force in. All right, so put your force vectors in, decide on friction direction based on one of those conditions I just discussed. Now you have to decide on what directions to write your equations in. So remember, this is a centripetal acceleration problem. The center of curvature is here. You have to decide in this picture which way that is. Keep it in mind that if the center of curvature was down here somewhere, the car would actually be going underground. So that should be enough to get you going on this problem. Draw a free body at some generic angle theta. Once you have a free body, you're going to write a pair of force equations, and I'll go ahead and tell you the directions. You're going to want to write one for this direction. I'm going to call that the positive x direction, one for this direction. And this positive x direction here will be parallel to your centripetal acceleration. So that should be enough to get this problem done. If you have any other questions with it, feel free to give me a call. Have a great day.